Without these fragile needles sticking out of a plane wing, your pilot might as well be flying a $200 million brick. They look like loose wires or broken antennas, but in fact are a crucial part of why flying is so safe today. Most people think the biggest hazard to a plane is a bird or a lightning strike, but there is an invisible adversary that grows more dangerous the faster the plane flies: the electron, a subatomic particle with a negative electrical charge. As the plane's skin rubs against air molecules and dust, it kidnaps billions of electrons. Trapped on the metal surface, these electrons hate being near each other. They want to escape because like charges repel. When a plane moves through rain, snow, fog, dust, ice crystals, or volcanic ash, this electrical charge builds up on the skin of the plane. Aviation calls this phenomenon precipitation static, or P-static. We often ignore the small things until they become a crisis. Just as small stresses can build up until you snap at your boss over a stapler, in aviation, this physical static builds up until it reaches millions of volts. Sometimes, the only way to handle the pressure is to find a way to let the small things go before they turn into a storm. The electrons eventually jump off the plane in uncontrolled bursts. Every time an electron jumps, it creates a tiny radio frequency interference pulse. Because billions are doing this at once, it sounds like a constant crackle or static hum in the pilot's headset that messes with the GPS receivers. Their chaotic jumping creates a wall of electromagnetic interference so thick that the pilot can lose GPS, weather radar, and the ability to hear the control tower. You're not crashing yet, but you are now blind and deaf in a metal tube at 35,000 feet. Flying through clouds or rain, and especially snow, acts like a giant charge generator. While friction with dry air, called triboelectric charging, still creates a charge, precipitation turns the volume up from a whisper to a shout. In physics, air is considered a fluid. Usually it acts like a wall, keeping electrons trapped, but when voltage exceeds a critical value, that wall crumbles. The corona voltage is the critical threshold where the electric field around a conductor becomes so intense that it actually ionizes the air around it. Ionization turns air into a conductor, like a wire, and the electrons form a bluish or purple glow, producing a hissing noise. This is called a corona discharge. The glow known as St Elmo's fire is usually formed around sharp objects like wingtips or antennas. In extreme cases, this buildup can cause a spark or damage equipment. Ancient sailors saw this glow on their masts and called it a miracle from St Elmo, the patron saint of sailors. Because the glow often appeared toward the end of a storm, sailors took it as a sign that their saint was watching over them. They viewed it as a good omen. Modern pilots see it on their windshields and realize they're about to go deaf on the radio. The physics hasn't changed, only our anxiety about it has. St. Elmo's fire isn't hot, it's low temperature plasma. While it looks cool, it's actually a warning. It means the plane's electrical pressure is so high that it's beginning to interfere with the magnetic fields around the antennas. It won't burn the plane, but it will blind the avionics. To save the plane, we need these thin needles called static wicks. Electrical charge naturally clusters around sharp edges. Because these carbon-coated rods are sharp and pointed, they create a high electrical field at the tip. The static wicks attract the electrons and allow them to leak off quietly and gradually, rather than waiting for a massive, chaotic discharge. The wicks essentially tell the electrons, if you want to leave, this is the easiest exit. By preventing that crackling noise, the wicks are protecting the nervous system of the aircraft, its ability to communicate, navigate, and keep information flowing clearly when the air itself starts turning noisy. Those tiny spikes are the plane's emotional release valve, and the clever part is where they're placed. You'll usually find them near trailing edges, the back edges of wings and control surfaces, because those are natural places for charge to leave the aircraft. It's like putting a tiny exit door for electricity in the most convenient spot. Static wicks are essentially decorative spikes unless they are properly bonded to the aircraft's surface. In other words, there must be a perfect conductive path that allows electrical charge to travel from every corner of the plane to the wick. Because that bond is so critical, pilots inspect these needles before every takeoff. They're looking for any corrosion or loose fittings that might break that conductive link and trap the electricity on the wing. If a wick looks charred or melted, it tells the pilot the plane was struck by lightning on a previous flight, signaling that the avionics need a deeper look. Fortunately, these wicks are designed to be easily swapped out for fresh ones, but in aviation, small doesn't mean cheap. Because these are FAA certified parts, made of specialized conductive materials that must maintain a very specific electrical resistance, they come with a sky-high price tag. A single wick for a commercial jet can cost as much as $400. That means a typical Boeing 737 is carrying about $15,000 worth of fuzz. Static wicks are built to survive 500-mile-an-hour winds, freezing temperatures at 40,000 feet, and the literal fire of a lightning strike. The smallest details are often the easiest to ignore, but on an airplane, even a tiny little whisker can be the reason the cockpit stays quiet enough to hear what matters. What's another detail on a plane you've always wondered about? Let me know in the comments. I'd love to investigate your suggestions for the next video. If you enjoyed this deep dive, hit the like button and subscribe to join our community. It helps the channel grow and ensures you won't miss our next documentary on strange histories of things we often overlook.